Hello back. We're going to talk about how to prepare beta-keto, beta-diketo compounds. There's a few that will be important for synthetic, um, you know, purposes. The first one is acetoacetone, which basically has two ketones, positions 1 and 3 in respect to each other. Technically, in this molecule, positions 2 and 4, right? But this molecule has an alpha carbon that is being sandwiched between two carbonyls, and that's kind of the key idea in this process. Now there's a couple ways you can go about making this molecule. You could envision, if you have a beta hydroxycarbonyl, to simply oxidize this to the diketone by using something like pyridinium chlorochromate as an oxidant. And the beta hydroxycarbonyl itself can be formed directly from the aldol condensation of that particular ketone, right? So you have a relatively simple way of getting to it, involving the chemistry that we've talked about in this lecture. Another way you could go about making it will be to first make the lithium enolate of your ketone under low temperature using, a lithium amide base, and then introducing your ester to undergo the condensation reaction, which will lead to this product. A derivative of the diketone is the ester nitrile, which, although this is not a carbonyl compound, it still withdraws electron density enough to make the alpha hydrogen, acidic enough. The way you can make this is by simply doing an SN2 reaction to the monobrominated ester with sodium cyanide. And you may recall the monobrominated product is something you can make easily via the Hell-Volhard-Zelinsky reaction, or alternatively through its derivative using thionyl chloride and alcohol to end up with the ester at the very end. So this is a very nice simple step to get to this molecule. Likewise, instead of the ester derivative, you could look at the ketone derivative, right? So cyanoacetone, same story, right? You could make the monobromination product simply by treating acetone with Br2 under acidic conditions. That will generate this monobrominated product, and then you can treat that with sodium cyanide to undergo the SN2 reaction, creating your cyanoacetone and leading to an alpha carbon that is sandwiched between two highly electronegative groups, at least decent electronegative groups that withdraw electron density. Okay, then we have the acetoester, which we've already talked about. Basically, the way you make that is via the Claisen condensation reaction, or alternatively, you could first make the enolate version of the ketone reacted with CO2 and then quench that with an alkyl to produce your final ester. But like I said, you could also introduce this from your Claisen condensation, or you could even do this follow-up reaction where you take the cyanoacetone derivative reacted with acid to turn the cyano group into a carboxylic acid, and then you can treat that with alcohol under acidic media to turn it into the ester, right? So you have a lot of options right here, right? Probably the most direct route will be the Claisen condensation, though. And then for this last one, which we're gonna talk a lot more in this lecture, uh, the dimethylmalonate or dialkylmalonate for general purposes. This particular molecule you can make either by first generating the enolate version of an ester and reacting that with carbon dioxide and finishing that off with an alkylation to give you the diester. Alternatively, you could take the ester nitrile, react it with hydronium and heat. That will undoubtedly turn your ester into carboxylic acid, but you will also turn the nitrile into the carboxylic acid. So at that point, you simply introduce the alcohol again to turn the carboxylic acids back into the esters. So you have ways of making these things, just to kind of be aware of the set of conditions. And the reason for that is because once you're sandwiching that alpha carbon, the acidity drops down considerably. And in the previous videos, I've been kind of just saying it, right? But now let me show you the numbers so you can see, how drastic an effect we're talking about. On the lowest end of the pK table for the regular organic molecules, you have your carboxylic acids. That's actually followed by nitromethane, which has a relatively low pKa due to the high electronegative withdrawing nature of the nitro group. But after that, the pKs jump, quite a bit, right? So the NH bond of an amide, that's at a pK of 15, which you can deprotonate with an alkoxy group relatively easily. By the time you get to your aldehydes, you're up to 17, ketones 20, esters 25, same as nitriles, and then the alpha proton of your amides are actually the least acidic of them all at a pK of 30. By the moment you get to this beta dicarbonyls, the pKs dropped considerably, right? In the case of acetoacetone, where you have two ketones sandwiching your alpha carbon, the pK drops down all the way down to 9. So you could easily deprotonate that hydrogen with hydroxide. And I'll make a point of highlighting that momentarily. For the ester derivatives, which donate a little bit more electron density than alkyls, the pKs go up a little bit, right? And you can kind of see the progression, right? If you only replace one of the alkyls with an alkoxy, the pK goes up, but only by a marginal amount. If you replace both of them by an alkoxide, then the pK goes up even more, right? And then you can see here that replacing the alkyl with a nitrile has roughly the same effect as the ester. So you have all the derivatives here that I'm including just for your general purpose, right, and your general information. But yes, replacing the carbonyl, ketone with a nitrile, increases the pK again, up to about 12. You have the cyanos, which are also in that vicinity, the low teens. But once you start introducing amides, the pK start jumping, to higher values. So in this class, we're not really going to talk too much about these diketo amides, but we will definitely talk about the esters and the ketone derivatives. So to that end, what I want to highlight is that the pK of your diketone is 9, right? And then for the esters, we're going up to 13, so it's not a huge jump. But compare that to your typical alkyl, right? We are removing a CH bond of an sp3 hybridized carbon, which normally for a regular alkane has a pK of 50. For an alkene, it drops down to 44. If the CH is bound to an actual double bonds, the pK, also drops down to 43. But if you instead of having an alkene have a carbonyl, the pK then drops considerably, right, all the way down to 17 for an aldehyde. So you have the inductive effect helping you out a lot. But the other thing that you have in your favor is that once you form this conjugate base, the resonance structure that leads to the enolates really helps you out, right? Because that carbon ion moves over to the carbon on the left. Those electrons move over to that oxygen to form this resonance structure. But conversely, those same electrons can move over to the carbon on the right side to form ultimately that resonance structure, that other enolate. And the fact that you have multiple ways of stabilizing the negative charge via resonance means that this molecule is a lot more stable, and the end result is that the pK drops down considerably. So you got extra resonance structures and you have extra inductive effects, all of them really helping out drop down that pK. And you can see like the difference between having an oxygen versus a carbon is not even like a little bit, it's huge. It's not even a fair comparison, right? All right, so yes, we have that stabilization. And then finally, this is the thing I want to make sure that we understand, is that as far as the pKs of these alpha hydrogens that are being sandwiched by the carbonyls, we could basically get away by using hydroxide as the base. This applies to the vast majority of these molecules, excluding the amides altogether. But when it comes down to the ester containing molecules, I already mentioned this during the Claisen condensations, but I'm going to mention it again. Although hydroxide will do the trick to deprotonate them, hydroxide will also attack the carbonyl carbon turning the esters into carboxylates. So you don't want to use hydroxide with ester derivatives. You want to use an alkoxide, and not just any alkoxide. You want to use an alkoxide that is basically the same one as the one in your ester. So yes, that's something to keep in mind. And yes, these reactions will go to completion as a result of that. Okay, so let's look a little bit about synthetically, what we do with these things. So let's say that we go with the malonic ester derivative. So this one is dimethyl malonate specifically. What you could do is deprotonate the alpha carbon being sandwiched between the carbonyls, and then you can introduce an SN2 substrate to it, such as this one right here. And what that will allow you to do is introduce one alkyl group into that alpha position. At that point, you could follow that up maybe with a slightly stronger base, bulkier base, to fully deprotonate that carbon. And then you can introduce another alkyl halide to then put a second alkyl group of your choice. And then here you have options. You could react this thing with acids, aqueous acids, under heating conditions to undergo a decarboxylation. And what it will do for you is that it will generate a carboxylic acid, not a ketone, but a carboxylic acid, because this is got two esters in its original moiety. So let me show you how this happens, right? So the first event is you deprotonate the alpha carbon, forming the corresponding enolate. That enolate is then introduced to the alkyl halide. So you reform the double bonds. The pi set of electrons here attacks the electrophilic carbon. The leaving group breaks off, and now you have your alkylated product, right? And you've already produced sodium chloride in the process. Okay, then you bring your second base, which could be a slightly bulkier base, to ensure that this fully gets deprotonated. So you deprotonate that hydrogen, you reform the enolate, and then you introduce the second alkyl halide. So the carbonyl gets reestablished, the pi bond attacks your electrophilic carbon, the leaving group takes off, and you get to your final dialkylated malonate derivative. So as far as the hydrolysis goes, you would be reacting this with water, right? And here I'm saving you the the steps to get to the carboxylic acid, but just between you and I don't know how that happens mechanistically speaking. But you can convert the esters into the carboxylic acids in acidic media. Now, if you, in addition of doing that, heat up the reaction, you have basically one of the carboxylic acids rearranging itself to have this hydrogen bonding situation happening. But then under high heating, there's an actual reaction that takes place. The electrons of the adjacent carboxylic acid attack this hydrogen. Those electrons move over to form carbon dioxide, which means that these electrons right here have to relocate to turn this into an enol, right? So you end up forming the enol derivative of the carboxylic acid. You kick out CO2 in the process. And then the last thing is that you simply tautomerize the enol that we have right here, right? You reform the carbonyl. The alpha carbon attacks the hydrogen of the acid that you have around, and you end up forming your protonated carboxylic acid, which then is deprotonated by the very water that you generated in that process. So this is how the whole thing takes place. It's kind of a pretty simple mechanism in terms of following the rules of your typical decarboxylation reaction. But it gives us a lot of really helpful stuff. And then the last thing that I'll mention before we move on to the next video is the decarboxylation enacted by Krapcho. This researcher did something pretty unique and interesting. So just to kind of highlight how cool this reaction is, first let me kind of summarize the ones that we've seen so far. You can take the beta-keto ester, react that with acids under heating conditions to decarboxylate the ester, and just end up with a corresponding ketone. We can do the same thing with the malonic acid ester derivative, right? Reacted with acid under heating conditions, one of the esters goes bye-bye, and the second ester remains as a carboxylic acid. And then this is where Krapcho comes in. He basically says, okay, well, great that we're starting with the esters and we can convert it into the carboxylic acids, but what about just removing the carboxylic acid without having to transform it? And that's what basically he ends up doing by treating your dimethylmalonate derivative with sodium chloride in DMSO. Okay, and here's a picture of Paul Krapcho, who designed the reaction from the University of Vermont. Basically, all that happens is that in DMSO, although sodium is solvated by DMSO, chloride is not. So it's basically a naked anion by all intents and purposes. And under the high heating conditions of DMSO, which we're talking 150 to 190 degrees Celsius, chloride attacks one of the methyls of the ester group. And the electrons of that oxygen carbon bond migrate over to the adjacent carbon to form carbon dioxide. What that means is that these electrons here have to relocate to the adjacent ester to form an enolate version of that. So you have a sodium enolate along with the alkoxy group there, but you also kick out CO2. So the last thing is, yeah, you just quench the reaction, right? So if you just introduce water, um, the enolate will simply reform the carbonyl, attack water, and get protonated, and then you have your ester back in the reaction. So it's a very elegant reaction for the carboxylations, and it's rather cool. And you can see how happy Paul Krapcho is about that reaction, because like it's really a delight. All right, so with that being said, let's end the video right here, and in the next one we'll start talking about micro additions. So catch you in the next video. Bye bye.